This lesson is going to get into the differentiation rules that I was talking to you about at the end of class on Friday. So a lot of that stuff that I mentioned about how we're going to be able to do these a lot faster to find the derivatives, you're going to start to see that happen over this lesson. So we're going to start pretty basic, work through some examples that hopefully you feel like, okay, I can do this. And then as we get to the end of this lesson, there will be some that will take some thought, take some time. Just kind of go slowly until you get a chance to practice some of these. So here are the objectives for today's lesson. All right, again, we're going to look at some of these basic rules to help us find these derivatives. And then kind of near the end of the lesson, we'll get into combining these rules to find the derivatives of more complicated functions. All right, so here's a few basic rules. All right, we have the constant rule that says that if you take the derivative of a constant, that you always get zero. This idea comes from the fact that if you have a constant graph, right, the graph of like y equals 2 is going to be a horizontal line, and the slope of that line, or the rate of change, is going to be 0. So that's why the derivative of a constant is always 0. All right, the power rule. This is the rule that I focused on when we were looking at some of these examples last Friday. So this says if you have a positive integer as your exponent, that is going to multiply, become the coefficient in front, and your positive integer exponent is going to be subtracted by 1. That's how we'll find the derivative of x to a positive exponent. All right, we'll practice that very soon. All right, let's start with the constant rule. Again, this should be pretty straightforward. Right, the idea is if you were to graph this, it's a horizontal line. So the derivative of a horizontal line, right, trying to find a line that's tangent to a horizontal line, the slope will always be 0. So if I do f prime of x is the same as d dx of 8, this is always going to be 0. All right, so the derivative of a constant is always 0. Now, this one is not going to be 0, right? This is the power rule. So we're going to find f prime of x equals d dx of x to the 10th power. So the way you want to do this is the 10, that's the exponent, is going to become the coefficient in front. Then you're going to write your x, and your new power is going to be 10 minus 1. So our derivative is going to be 10x to the 9th power. All right, so that's called using the power rule. All right. Now, here are some more rules that probably make a little bit of sense in terms of your experience with different types of theorems in algebra. But essentially, if we're trying to find, the derivative of two functions added together or subtracted together, we can just find the derivative of the first one and the derivative of the second one, and then either add them or subtract them, depending on what we're doing. Another rule that we'll go over is called the constant multiple rule. I'll be honest, I don't really use this one much, just because if there's already a constant, I just multiply it by whatever I'm bringing down. Like in this last problem, if it had like 2x to the 10th power, that 10 would just be multiplying by that 2 to make it 20x to the 9th power. So I'll go over the constant rule, but I think you'll find that one is probably superfluous in terms of not really using it. Okay, so let's try this one. We're going to find the derivative of 3x squared, which is d dx of 3x squared. Okay. Now, using the constant rule, what we would do here is we would do 3 times d dx of x squared. All right. Again, so you're just bringing the 3 in front along for the ride. That's going to be 3 times. So if we're using the power rule for x squared, that's 2x. And then we have 2 minus 1 power. So that's 3 times 2x, right? Because 2 minus 1 is 1. So the answer is 6x, right? That is the derivative of g prime of x. Or I should say the derivative of g of x, which is g prime of x. And again, the way that I do this is I just take the 3, multiply by the 2 to give me that 6, and then subtract the exponent by 1. So I don't really use the constant rule that much. I just kind of put it all together. All right. Comparing it to the derivative of f of x, right? The derivative of x squared, as we just found out, is 2x, right? Highlighted here. All right, so it's 3 times the derivative of the x squared, right? The derivative of g of x is 3 times the derivative of f of x. So if you were to graph it, you would notice that your slope is 3 times steeper. Okay. Let's use some basic derivative rules. This is using the sum rule. So if we're trying to find the derivative of f of x, we're going to do d dx of 2x to the 5th power plus d dx of 7. Again, we kind of talked about this on Friday. So we're using the power rule. Again, I'm not going to do the constant multiple rule. You can if you want. I just think it's easier just to kind of do it all at once. 5 times 2 makes 10. Subtract 1 from 5 and you get x to the 4th power. Plus the derivative of a constant, as we talked about in our very first rule, is 0. So the derivative of f of x is 10x to the 4th power. Okay, this one. I really like this question. I know we've done so many examples in this class, so many different problems, but we did this problem last week in a lesson where we had to find the equation of a line that's tangent to this graph at a certain point. And we did this using limits, and it was a long formula. It took a long time. And then we even had to find, using point slope form, had to find the equation. So we're going to do that same process, but now we're not going to use any limits. We're going to use our derivative rules to actually find the slope, if you will. Okay, so the first thing I'm going to need, I guess it doesn't need to be the first thing, but I'll do it first, is to find the equation of a line. I am going to need a point and a slope. And they've already given me one part of the point, right? They give me x equals 1. So to find the rest of the points, I'm going to do f of 1. So 1 squared minus 4 times 1 plus 6. That's 1 minus 4, which is negative 3. Negative 3 plus 6 is positive 3. So my point is 1, 3. Now, to find the slope of this curve, right, it's a parabola. To find the slope of this tangent line that's hitting this curve at x equals 1, I need to find the slope, right, of that line at x equals 1. So the way I'm going to do that is I need to find the derivative of the function, which is going to be d dx of x squared, minus d dx of 4x plus d dx of 6. So first I'm going to find the derivative. So that's 2x minus 4. And you could write plus 0 if you wanted to. All right, but you don't need to, right? The derivative of that constant 6 will be 0. And then to find the slope, I'm going to plug in 1, right? I'm plugging in x equals 1 to find the slope at for the tangent line at this point. So 2 times 1 minus 4 equals 2 times 1 is 2. 2 minus 4 is negative 2. So that is the slope. So now I have my point, right? I have my point. I have my slope. So now I can use point slope form to find the equation for this line. So y minus y1 equals m times x minus x of 1. Y minus 3 equals negative 2 times x minus 1. Distribute the negative 2. So negative 2x plus 2. So our equation is negative 2x, and that's going to be plus 5. Okay, so let me do the same thing I did when we did this example, with completely different work, but we did got the same answer in terms of finding that line. So if I graph my parabola, x squared minus 4x plus 6, all right, so we have x squared there it is, minus 4x plus 6, okay? There it is, x squared minus 4x plus 6. And I'm also plotting my line, which is negative 2x plus 5. You can see Look up here, right? This point 1, 3, there's my point 1, 3. And that blue line is the line that is tangent to this red curve at the point x equals 1. All right, so just kind of putting it all together in your brain of like what we were doing there. Okay, let's keep going. Some more rules. This is the product rule. All right, now this one is a little bit tricky here when you do this, but make sure you're really focused on what we're doing. To find the derivative of two functions that are multiplied together, you find the derivative of the first one and multiply it by the original second, and then add the derivative of the second one times the original first one. All right, so it's going to take a little practice here. As I said, like this point in the lesson, we're going to start to get a little bit more complicated in some of the rules that we're using. Okay, so let's try this example. It says j of x is f of x times g of x. All right, so I'm literally just going to use this right here since they've given me f of x times g of x. Try that again. There we go. So I'm going to write that down. So j prime of x, right, to find the derivative of this function is going to be f prime of x times g of x, right, the derivative of the first times the original second, plus the derivative of the second, so g prime of x, times the original first one. All right, now this wants me to do j prime of 2, so that's going to be f prime of 2 times g of 2 plus g prime of 2 times f of 2. Replace all those values you just put in there with the actual work that they want. So f prime of 2 is negative 4 times g of 2 is 1 plus g prime of 2 is 6 and then f of 2 is 3. So that's going to be negative 4 plus 18, so j prime of 2 is 14. Now, most likely, I mean, maybe, right? I haven't taken the AP Calc exam since I was in high school many years ago, but I'm interested to see how they ask some of these questions, especially on the multiple choice. Okay, let's try this one. Okay, we're going to find by the product. We're going to use the product rule to find the derivative here, and then just for fun, we're going to check the results by actually multiplying this all out and then differentiating. So you're going to see kind of which way would you rather do, right? Again, if this is a question on the AP exam, it just says find j prime of x, you've got two options. You can distribute it all out first and then find the derivative using kind of the sum rule, which is probably faster, or you can use the product rule since it is two functions multiplied together. So again, I'm going to write down that formula. J prime of x is equal to the first one, right? First derivative, the derivative of the first function times the second plus the derivative of the second function times the original first function. All right, so here we go. That means I'm going to do the derivative, so d dx of x squared plus 2 times 3x cubed minus 5x plus d dx of the second one, which is 3x cubed minus 5x times x squared plus 2. All right, here we go. The derivative of x squared plus 2 is going to be 2x plus the derivative of 3x cubed minus 5x is 9x squared minus 5 times x squared plus 2. So now it just becomes, at this point, an algebra problem, right? We're distributing and combining like terms. So this is 6x to the fourth power minus 10x squared plus 9x to the fourth power plus 18x squared minus 5x squared minus 10. All right, let's get all our like terms. Let's see if we've got x to the fourth powers. So 15x to the fourth power So negative 10 plus 18 is 8. 8 minus 5 is 3. So plus 3x squared, and then minus 10. All right, so let's confirm, right? This is what I think the answer is for j prime of x. Well, we're going to check this. I'll change colors by first distributing, right? Taking this j of x function and distributing, and then finding the derivative once we distribute it. So that's going to be j of x equals 3x to the 5th power minus 5x to the 3rd power plus 6x to the 3rd power minus 10x. Okay, let me get some like terms. 3x to the 5th power plus 1x cubed minus 10x. So now if we find the derivative, we're just using the sum rule, right? So I guess I'll stick with blue. To find j prime of x this way, we're doing d dx of 3x to the 5th power plus d dx of x cubed minus d dx of 10x to the 4th power. All right, let's confirm. This is 15x to the 4th power plus 3x squared, and then this is going to be, oh, that's not x to the 4th power, Douglas, my bad, sorry about that, minus d dx of 10x is going to be minus 10. And that confirms, right? We got the same thing. So it's your choice. Again, if this were an AP Calc question, you've got, or I should say AP exam question, then you've got options. All right, let's keep going. All right, some more rules. Now, we just did the product rule. Here's the quotient rule. All right, the quotient rule is a little bit tricky. There are some similarities to the product rule, but the quotient rule, is going to be the derivative of the numerator times the original denominator minus the derivative of the denominator times the original numerator over the derivative, over the denominator squared. Okay, it's up to you on which you prefer. I think a lot of students that I'm going to teach are going to prefer the second way to write this, just because it feels more like algebra. But don't be afraid to try using Leibniz's notation, which is ddx. Okay. Let's use it for this one here. So I'm just going to follow along with either the first one, right? This one or that one, doesn't matter. So we need to find, so let's do k prime of x is going to be ddx of the numerator, so 5x squared, times the original denominator minus ddx of the original denominator times the original numerator, all over the denominator squared. All right, let's do a little work here. The derivative of 5x squared is 10x. So 10x times 4x plus 3 minus, all right, and the derivative of 4x plus 3 is just 4 times 5x squared all over 4x plus 3 squared. Keep going. We're going to distribute here. 10x times 4x is 40x squared plus 30x minus 20x squared all over 4x plus 3 squared. So my answer for k prime of x is going to be 20x squared plus 30x all over 4x plus 3 squared. Okay, you can factor out an x if you wanted to in the numerator, but you're not going to be able to. I guess you can factor out a 10 as well. Then you get 2x plus 3. That's not going to be able to cross out with anything. Oh, excuse me. So this is fine, just to leave it as is. Okay. Now this next power rule, again, this is one when I was learning calculus, I kind of just ignore this. What I end up doing is just using that same power rule from before. It's just if you have a negative exponent, all that means is the negative exponent is going to become your coefficient, and you still have to subtract the power minus 1. So it's actually very similar to what we did before. It might look a little different. So it's going to be negative 4 times x to the negative 4 minus 1 power, which is negative 4 to the x minus 5 power. Now, if you wanted to write that with a positive exponent, it'd be negative 4 over x to the 5th power. Both of these are the same thing. Okay, now I will say, and I'll kind of show you with an example later, that your understanding of if it gave it to you as a rational function where you have your variable in the denominator, just that, I'm going to change it to look like how this was written, so that way I can just use the extended power rule as opposed to the quotient rule, right? Remember, the quotient rule we just did, right, this example, I'm going to try to avoid that as much as I can, because that's a lot more work than just using this power rule. All right, so let me kind of give you an example to go with what I just said. You can do the quotient rule here, right? You have a numerator, you have a denominator, but there's no reason to. Go ahead and rewrite this as 6 times x to the negative 2nd power, right? Move the x squared to the top. It has a negative exponent now. So now to find the derivative, I'm going to do d dx of 6x to negative 2nd power, which is going to be negative 12, right? Negative 2 times 6 is negative 12. X to the negative 2 minus 1 power, which is negative 12 times x to the negative 3rd power. So that is my derivative. Again, if you want to write it as negative 12 over x cubed, that's fine. It does not matter to me. Okay, now we're going to start to combine some rules. I think like this is kind of the third part, or third chapter of this lesson, where it starts to get a little tricky. All right, so even as I was reviewing of how to go through these, I'm having to stop and really focus and figure out, okay, what am I doing here? Because you are combining these rules. A good rule of thumb, and I'll show you in the book here. A good rule of thumb. Let me get to it almost there. Wait for it. Here we go. If you look at one of the lines here, the last line of this paragraph where it says combining differentiation rules, it says a good rule of thumb to use when applying several rules is to apply the rules in reverse of the order in which we would evaluate the function. Okay, so just kind of keep that in mind. We're going to kind of, instead of using PEMDAS, or think like, okay, what would I do for PEMDAS? I'm going to go backwards in terms of doing my rules. All right, so let's try this one. We're doing k prime of x, and k of x is 3 times the h of x function plus x squared times g of x. So to do k prime of x, I'm going to do, this is first the sum rule, d dx, right? Again, if we were doing order of operations, we would do this last. But I'm going to do d dx of 3 h of x plus d dx of x squared times g of x. Okay? Now, the first one, or I should say like the piece on the left, I don't think it'll be too bad, right? If you need to use the constant rule, you can. But essentially, this is going to be 3 times h prime of x. All right, so that one's done. All right, plus, though, if you look at this on the right side, d dx of x squared times g of x is actually going to need to be the product rule, right? We have two functions, so I need to do the derivative of the first times the original second plus the derivative of the second times the original first function. So I'm going to put this kind of in a bracket. I've got d dx of x squared times g of x plus d dx of g of x times, let me use this one, times x squared. Okay, so let's do work there. The derivative of x squared is 2x, so that's 2x times g of x plus the derivative of g of x is g prime of x times x squared. Okay, I'll bring this down. And I think we're ready to write this out. So 3 times h prime of x plus 2x times g of x plus x squared times g prime of x. All right, and that is the derivative. I know this can feel a little bit tricky because we don't actually have real functions, right? They're just having it show with the notation. But ultimately, this is what I'm looking for when you combine these different differentiation rules. All right, I'm going to pause for a moment just to make sure that I got that one right. Okay, so I got that one correct. Awesome. Now we're going to move into another one where we are doing some combination here. The tricky thing about this is that you actually have three functions, but the way we're going to do this is I'm going to treat this as two functions multiplied together, where the first function is f of x times g of x. So I want you to think of this as k of x is the same as f of x g of x, which is one function, times h of x. So to find k prime of x, all right, I'm going to first do d dx of f of x times g of x, all right, times the original h of x, right, plus d dx of h of x times my other function, which is f of x times g of x. Okay, now the problem here, not problem I should say, but what makes this tough is that if you look at find the derivative of f of x times g of x, we now have a product rule that's within a product rule, right? We just applied the product rule of this function times this function, but now we've got to do another product rule to deal with this product, okay? So that's going to be d dx, put this in parentheses here, or a bracket, d dx of f of x times the original g of x plus d dx of g of x times the original f of x. But remember, that's all inside being multiplied by this h of x. Okay? Close that. Plus, and this one you can probably notice it's a little bit easier. D dx of h of x is just h prime of x times f of x and g of x. Okay? Now let's deal with this bracket. So we have the derivative of f of x, which is f prime of x times g of x, still inside this here, plus the derivative of g of x, which is g prime of x times f of x. But all of that needs to be multiplied by h of x. Copy this down, h prime of x times f of x times g of x. Okay, so I'm going to distribute now this h of x here, right? I'm going to distribute this h of x to get f prime of x times g of x times h of x plus g prime of x times f of x times h of x plus h prime of x times f of x times g of x. So that, I know that was a lot of work there, is the same as k prime of x. Okay, so this was an example of a product rule within a product rule. So two instances of the product rule in the same problem. Okay? All right, let's go to the next one. All right, so this is going to be combining the quotient and the product rule. All right, so the first thing that I'm going to do is I'm going to apply the quotient rule since we have that. So to find h prime of x, right, this is the quotient rule first. So it's the derivative of the numerator, so d dx of 2x cubed times k of x, all right, times the original denominator, 3x plus 2, minus the derivative of the denominator, so 3x plus 2, times the original numerator, which is 2x cubed times k of x, all over the denominator squared. Okay. Now, again, that's just the quotient rule. But if you notice, the first part that I wrote is we have d dx, so the derivative of 2x cubed times k of x means we have to do the product rule in there, just like we did on the previous one. So here we go. We got the product rule now. d dx of 2x cubed times the original k of x plus the derivative of k of x times the original 2x cubed, right? Again, all of that still needs to be multiplied by 3x plus 2. I'm going to close that off and subtract, do a little work here. The derivative of 3x plus 2 is just 3, so minus 3 times 2x cubed times k of x. Okay, and that's still all over 3x plus 2 squared. Okay, let's do a little cleanup here in the numerator. The derivative of 2x cubed is going to be 6x squared. So that's 6x squared times k of x. Still put this in here. Plus the derivative of k of x is k prime of x times 2x cubed. And all of that needs to be multiplied by 3x plus 2. Minus, do a little more distributing, we get 6x cubed times k of x all over 3x plus 2 squared. Okay, now I'm going to distribute the 3x plus 2 times the two pieces in these brackets here. So 3x times 6x squared k of x is going to be 18, let's see, so 18x cubed times k of x plus, I'm going to do the 3x times the second part, which is going to be 6x, let's see, what would make more sense for everyone's brain? Probably to multiply the first term by that one. Okay, so let me start over. So I'm still doing this 6x squared k of x times this 3x. And now I'm going to do that 6x squared times k of x times the 2. So that's going to be plus 12x squared times k of x. Okay. Plus, now I'm going to redo this with the k prime of x times 2x cubed times each of those pieces. So k prime of x, 2x cubed times 3x is going to be 6x to the fourth power times k prime of x plus multiply by 2, and we get 4x cubed k prime of x minus 6x cubed times k of x. And don't forget, all over, oh my goodness, all over 3x plus 2 squared. Okay, I don't think I have any like terms. Let me just check. Oh, I might actually have some like terms here. Cool. So let's see. This one has x to the fourth power, so I'm going to write that first. Then I do have some x cubes, but I need to make sure they have the right k of x and not k prime of x. So it looks like the only like terms I have are going to be the minus 6x cubed k of x and the 18x cubed k of x. So those are going to be like terms. So I'm going to write the answer as 6x to the fourth power. Actually, you know what? I think let me check. I'm going to pause for a second. I think they wanted me to write in standard form with the derivatives of k of x last. Let me just confirm that. Yes, so the way they do it to finish it is they don't actually put those ones that I highlighted together. They leave them separate, and they put the k of x first. So we have 18x cubed k of x minus 6x cubed times k of x plus 12x squared times k of x plus 6x to the fourth power times k prime of x plus 4x cubed times k prime of x. all over 3x plus 2 squared. All right, so there was an example of the product rule within a quotient rule, and that's going to be all equal to k prime of x. I just like h prime of x, my bad. All right, let's keep going. We're almost done. Now, determining where a function has a horizontal tangent line. I'll refer to this in class, but if you go back to your notes, and I'll just show you here. If you go back to your notes from the last lesson, when we did some graphing right here, all right, we sketched the graph of the derivative of the original function. And you'll remember, maybe you don't, but if you remember, one of my key things that I do is I look for the horizontal tangent lines on the original function. Because remember, when you're graphing the derivative, you're graphing the slope of those tangent lines to the original curve. And if they're horizontal tangent lines to the original curve at a certain point, then those are going to be the zeros of the derivative, right? So that's why I had a 0 here and a 0 here. So this question essentially is, if you know that, right, if you understand that, then to find the values for f of x where there's a horizontal tangent line, we're going to find the derivative of this original function. So we're going to find f prime of x. And we're going to solve that derivative, set it equal to 0. So if we find the zeros of that derivative function, then we will have the values for x that have a tangent line to the original curve, original function. All right, so here we go. I'm going to do this much quicker because this is just using the sum rule, find the derivative of each of these. The derivative of x cubed is 3x squared. Derivative of negative 7x squared is negative 14x. Derivative of 8x is 8, and the derivative of a constant 1 is 0. So if I solve this, so 3x squared minus 14x plus 8, I'm going to try to factor it. So let's do factors of a times c that add to b. So 3 times 8 is 24. B is negative 14. So I'm looking for factors of 24 that add to negative 14. So that's going to be negative 12 and negative 2. So if I rewrite those, I have 3x squared minus 12x minus 2x plus 8. We're going to factor by grouping. Factor out the 3x, you get x minus 4. Factor out the minus 2, you get x minus 4. So my two factors are 3x minus 2 times x minus 4. Set each of those equal to 0, and you get x equals positive 2/3 and x equals positive 4. So those two x values, I should say, are going to be where your horizontal tangent line would be happening. So let me show you on Desmos. So hopefully this will help your brain understand kind of what I just did there. Almost done, so close. So we have x cubed minus 7x squared, x cubed minus 7x squared plus 8x plus 1. All right, so if I zoom in on this point here, which is the relative maximum, all right, you'll notice that x value is 0.667, which confirms my 2/3 there. All right, and my other relative extrema, minimum or maximum, is down here. Right, the horizontal tangent line would be at 4. All right, so we can see that we have x equals 4 for the other one. All right, so just going to show your brain essentially why we're looking for those horizontal tangent lines. Okay, those two there. Okay, almost there. Let's keep going. Last one, and then we'll be done. All right, we have the position, the position of an object on a coordinate axis at time t is given by this position function, t over t squared plus 1. What is the initial velocity of the object? So to do this, right, as I mentioned last week, it goes position function, then the derivative of that is velocity, and then the derivative of that would be the acceleration. So in this case, to find the initial velocity, I need to find the velocity function. So I'm going to find the derivative of the position function, that would be the velocity function, and I'm going to plug in 0, right? Initial velocity would be at time 0. Okay, so let's find the derivative. I'm going to be using the quotient rule for s prime of t. So that's going to be the derivative. So d dx, I guess I should say d dt of t times t squared plus 1 minus dt of t squared plus 1 times t all over t squared plus 1 squared. Okay, the derivative of t is going to be 1. So 1 times t squared plus 1 is just t squared plus 1 minus the derivative of t squared plus 1 is going to be 2t times t all over t squared plus 1 squared. So that's going to be t squared plus 1 minus 2t squared over t squared plus 1 squared. You could write it in, actually, we have like terms. Let's do that. My bad. So this is going to be negative t squared plus 1 all over t squared plus 1 squared. All right. We're going to plug in 0, right? That's the velocity function. So I'm going to plug in 0 and get the opposite of 0 squared plus 1 over 0 squared plus 1 squared, which is 0 squared is 0, the opposite of 0 is 0, 0 plus 1 is 1, 0 squared is 0, 0 plus 1 is 1, 1 squared is 1. So the initial velocity is 1. Doesn't say any units, so 1 meters per second if we're going to keep with the physics idea. All right, so that shows you an example of an application of your understanding of going from position function to velocity function to acceleration function. All right, okay, hopefully you'll feel good about this. Some of these were pretty tough, but ultimately we are finally able to use some differentiation rules.